Hey there, and welcome. Today, we are diving deep into what is basically the secret language of chemistry, chemical reactions and equations. This is the code that describes all the incredible transformations happening around us and even inside us, from a bike rusting outside to the food we eat becoming energy. Let's jump right in.
All right, to kick things off, let me ask you something. Think about rusting iron, baking a cake, and a cozy campfire. They seem totally different, right? Well, believe it or not, they're all just different flavors of the very same fundamental process. And by the end of this, you'll see exactly how they're all connected. So here's our game plan for today. We're going to start with the absolute basics. What even is a chemical reaction? Then we'll learn the shorthand chemists use to write them down. After that, we'll cover the one rule you can't ever break. We'll meet the main types of reactions you'll run into, and finally, how to spot them happening in real life.
Okay, first things first. Before we can start writing all those cool-looking equations, we have to get on the same page about what a chemical reaction really is.
And here's the core idea. A chemical reaction is just a process where your starting stuff, which we call reactants, gets totally rearranged to become brand new stuff, which we call products. Now, the most important part here is that the products are completely new substances with totally different properties from what you started with.
Now, it's super easy to get this mixed up with a physical change, so let's clear that up. When you melt an ice cube, it's still H2O, right? It just changed from solid to liquid. That's a physical change. But when iron rusts, you don't have iron anymore. You've got a new, flaky, reddish substance called iron oxide. That's a chemical change, and that's what we're talking about today.
And this picture, it's the perfect example. That reddish-brown rust on the chain isn't just a coating. It's not the strong, shiny metal it used to be. It's a fundamental transformation, all the way down to the atomic level. A brand new substance has been created. Okay, so we have these incredible transformations happening, but how do we describe them without, writing a whole novel every single time? Well, luckily for us, chemists came up with a kind of special shorthand, the chemical equation. We could just write it out in words like magnesium plus oxygen makes magnesium oxide. And that's fine, it gets the point across. But chemists need a universal language that works everywhere. So we level up to what's called a skeleton equation. We just swap the words for the official chemical symbols. It's way faster and tells the exact same story. Every single equation you'll see has two main parts. On the left side of that arrow, you've got your reactants. Think of them as your ingredients. And on the right side, you got the products, what you made. Simple as that. Okay, now we get to what is without a doubt the single most important rule when writing equations. It's not enough to just list your ingredients and what they become. You have to make sure every single atom is accounted for. This is called balancing.
And you might be sitting there thinking, okay, but why? Why the extra work? Can't we just leave the equation as it is? It's a really good question. The answer is one of the most fundamental laws of the entire universe, the law of conservation of mass. All it really means is that in a chemical reaction, you can't just create atoms out of thin air, and you can't have them just vanish. They're only rearranged. So the number and type of atoms you start with has to equal the number and type of atoms you end with. No exceptions.
So how do we actually do it? Well, it's a pretty straightforward three-step process. First, you write down your basic, unbalanced skeleton equation. Second, you do a quick inventory. Count up all the atoms of each element on both sides of the arrow. Then, third, you use big numbers out front, called coefficients, to make the counts match up. The one thing you can't do is change the small subscript numbers, because that would change what the substance is. Okay, so we know what a reaction is, and we know how to write and balance the equations. Now, let's meet the main characters. While there are like a bazillion different reactions out there, almost all of them fall into just a handful of major categories. I like to think of these as the basic plot lines for chemical stories. You've got your getting together story and your breaking up story. You've got a simple swap, and then you've got a more complicated partner exchange. These basic patterns cover almost every reaction you're going to see. Let's take a quick look at each one. First up, the combination reaction. This one is exactly what it sounds like. Two or more simple things, like hydrogen gas and oxygen gas, come together to form one single, more complex thing. In this case, water. Simple and clean. And decomposition is, you guessed it, the exact opposite. Here, one complex compound breaks down into two or more simpler parts. For instance, if you zap water with enough electricity, you can split it right back apart into hydrogen and oxygen gas. In a displacement reaction, you have a more aggressive or reactive element that basically comes in and kicks a less reactive element out of its compound. Here, zinc is more reactive than copper, so it swoops in, boots the copper out, and takes its place. Poor copper is left all by itself. And finally, we have double displacement. The best way to think about this one is like two couples on a dance floor swapping partners. The silver decides to dance with the chlorine, and the sodium pairs up with the nitrate. Everybody gets a new partner. Often, this creates a solid that falls out of the solution, which we call a precipitate.
So, that's all the theory. But let's get practical. How can you tell if a chemical reaction is actually happening right in front of you? I mean, you can't see the atoms moving around, but you can look for a few telltale signs.
All right, here are the big 5 clues that some chemistry is going down. You might see a permanent color change. You could see bubbles of gas being formed. You might feel it get hotter or colder. Or you might see a solid suddenly appear in a clear liquid. That's a precipitate. A change of state can also be a clue. And once you start looking, you see these signs everywhere. The incredible colors of autumn leaves, that's a whole series of chemical reactions breaking down chlorophyll. And in a lab, if you mix two things and suddenly see a bunch of fizzing and bubbles, that's a dead giveaway a reaction is happening. Oh, and a change in temperature? That is a massive clue. The reason a fire feels warm is because burning wood is a classic exothermic reaction. It's releasing a ton of energy in the form of heat. If something feels cold, it's an endothermic reaction, sucking heat in from its surroundings.
So to wrap all this up, I want to leave you with this final thought. You're not just some passive observer of chemical reactions. You are, right now, a walking, talking, thinking collection of trillions of them. The very act of you watching and understanding this involves countless chemical reactions, from digesting your last meal for energy to the neurons firing in your brain. Chemistry isn't just something that happens in a lab. It is you.